Alright, so let's examine the first law of thermodynamics at constant pressure. Once again, we start with the first law, du equals dq plus dw. And at constant pressure, there's a few things that we need to consider. This is probably the more convoluted out of all the cases. At constant pressure, the heat is given once again by the number of moles of the substance multiplied by the heat capacity. But this time around, this is the heat capacity at constant pressure because the pressure is constant. And that also gets multiplied by the change in temperature. So this setup for heat doesn't change all that much. Now work, on the other hand, because the work is constant, negative P dV is the same thing as negative P times V final minus V initial. Right? And we know that equation to be true because the pressure is constant. Alright, now finally, du, as I explained on the last example, is always going to be given by the moles times the heat capacity at constant volume times the change in temperature. But in a setup where the pressure is constant, you're not going to have CV. Instead, you're going to have heat capacity at constant pressure. And you're going to have this whole setup. So technically speaking, the internal energy is going to equal dq, which is ncp dt, plus the change in work, which is negative P times V final minus V initial. Now that whole thing is equal to the internal energy. And one thing that I want to point out right here, since subtracting the pressure times the change in volume from ncp dt is equivalent to ncv dt, what this is telling us is that the heat capacity at constant pressure is actually larger than the heat capacity at constant volume. Okay, so something to keep in mind, not necessarily something on a test shown, but I kind of want to make you aware of that. For this problem though, to get the changing internal energy, yes, you're going to have to get the changing work, changing heat, add them together, and together they will be the changing internal energy, as you will see in the next example. Alright, so now what we're dealing with is half a mole of a gas. The volume is changing from 1.25 liters to 3.75 liters. We're performing this at constant pressure. The pressure happens to be 1 atmosphere, but it is constant. Okay, so now we need to, and we're given the heat capacity at constant pressure, 2.88 joules per mole Kelvin. So we're going to need to calculate all these things. Now, as I said, start by calculating the change in work. That's usually the first thing, the most trivial thing to do. But for the sake of aesthetics, I'm actually going to start with the changing heat. Either or, you're going to have to do both. But I recommend that you start with work, get the value first, then determine whether you have to calculate du or dq. Now in this case, we're going to go after dq because we don't have CV. All we have is Cp, right? So dq is going to be given by the number of moles multiplied by the heat capacity at constant pressure multiplied by the change in temperature. And you might actually stop for a second and be like, okay, that seems simple enough, except for one crucial detail. We don't have the temperatures. What are the temperatures? We don't actually know. So here you have to do an extra step. And this extra step is to basically go based on the premise that you're dealing with gases, specifically ideal gases. And I kind of gave it away right there. What you're basically going to do is find out what these temperatures are, even though you weren't given the temperatures, by using the ideal gas law, PV equals nRT. Therefore, the temperature is going to be given by PV over nR. And right now, since you have the final volume and initial volume, you can calculate the final temperature and initial temperature in much the same way, PV divided by nR. So, for the final temperature, we have a pressure, which is constant at 1 atmosphere, a final volume of 3.75 liters, N is still 0.25 moles, and R is a constant, 0.08206. So using all those parameters, we'll cancel out everything except for Kelvin, the units of temperature. The same is done for the initial volume. The initial volume is 1.25. Everything else in the equation remains the same. 1 atmosphere, half a mole, 0.08206 atmosphere liter per mole Kelvin. So the volume is the only thing that changes. And what you find out with this is that the final temperature is going to be 91.4 Kelvin. The initial temperature is 30.5 Kelvin. Alright, so this is the only extra step that needs to be performed here because you weren't given the temperatures to begin with, but you did know the changes in volume. Okay, with everything at hand, we can now perform the calculation. Half a mole multiplied by the heat capacity constant pressure, which is 2.88 joules per mole Kelvin, times the change in temperature, 91.4 minus 30.5 Kelvin. Kelvins cancel out, moles cancel out, and you end up finding out that the change in heat is 87.7 joules. Okay, so simply increasing the volume while keeping the pressure constant increases the amount of heat that your gas now has. All right, now let's take a look at work. This, as I said, is probably going to be the first thing that you calculate, but for the sake of aesthetics, I decided to do it first. Excuse me, do it second. All right, now the pressure is constant, so we know that the work is going to be given by the negative pressure times the change in volume. We know that V final is 3.75, and we know that V initial is 1.25 liters. The pressure itself is 1 atmosphere. So we're going to input all of those values, and we're going to get for the difference 3.75 minus 1.25, that's 2.5 liters. Multiplying that by 1 atmosphere gives us negative 2.50 atmosphere liters. What you want to do now, and this is actually kind of important in terms of keeping the units around. Notice that this is not the same thing as joules. So what you really want to do is multiply this by 101.325 to get the number of joules. That will now be negative 253, and the units are the same as those of heat. Right? You want these two units to be the same because otherwise finding the internal energy is going to be total shenanigans with atmosphere liters. All right, so now that we have the heat and we have the work, we simply combine them together. We have 87.7 joules for the heat and we have negative 253 joules for the work. So we add them together and we find out that the internal energy is negative 165 joules. All right, and by doing all of that, we have gotten the heat, the work, and the internal energy. So this is a little bit more work because you have to perform actual calculations for heat, actual calculations for work, and then utilize that to get the internal energy itself. Okay, one more parameter to look into, constant temperature. All right, so starting with the first law once again. One thing that I did mention in a little earlier is that the internal energy depends fully on temperature. Specifically, it depends on moles times heat capacity constant volume times change in temperature. If the temperature, however, is constant, then automatically the internal energy is 0. There is no change in internal energy because the temperature is constant. And for the work, what we do know is that, okay, well, negative PdV is the work, but in the absence of any other data, what we need to assume is that the pressure is variable. However, if we're told that the pressure is constant, then we still use negative pressure times the change in volume. When the pressure is variable, however, we use negative nRT ln of the ratio of volumes. So depending which one you use, it really depends on the characteristics of the problem itself. But if the pressure is not mentioned in the problem, assume that it is variable. Now the heat itself is going to be given by the opposite of the work. Since the internal energy is going to be 0, dq will have to equal negative dw. And depending upon which setup you have, you could have negative P times change in volume, or you could have negative nRT times ln of V final over V initial. In any case, you're going to find out what the value of the work is. Simply put a negative in front of it, and that will yield the change in work. All right, so let's give you an example. We want to determine the total value of du, dq, and dw for 0.333 moles of gas. The temperature is raised. Temperature raised. Actually, the temperature is constant, so that's a little it's a little woo-woo right there. the temperature is 273 Kelvin. The volume is changed from 0.554 liters to 2 liters. Okay, so we're going to start with the work. And we know that this is equal to negative nRT ln of V final over V initial. Okay, so we know that number of moles is 0.333 moles. The gas constant is 8.3145 joules mole Kelvin. The temperature is 273 Kelvin. And the final volume is 2 liters. The initial volume is 0.554 liters. Okay, so perfect. The liters cancel out. You carry out that division, followed by the natural log. You multiply by 273, multiply by 8.3145, and multiply by negative 0.333. That should yield negative 970 joules worth of work. Alright, now, we know that at constant temperature, the internal energy is going to be 0. So what this tells us is that the change in heat is going to be equal to 0 minus the works, in other words, minus 970, or 970 itself. So the heat itself is going to be 970 joules. And okay, with that, I think we're done with all the examples involving the first law of thermodynamics. In the next video, we'll talk about heat, enthalpy heat.